So, hello and welcome to today's PoC-2 webinar. As you can see, we have a premiere. We are together in one room. So, hello here and here. Okay, so my name is Anna Kassin and I'm your host today. And today is the first part of our webinar series about the PoC-Library. It's a free and open source VHDL package and component library. So, and before we get started with the webinar itself, I want to talk about a few general topics here. And I will start with the first slide. So, this webinar is about 1 hour, including Q&A at the end with your personal questions. And then we have a recorded session. So, this means we will send out a follow-up email to you with the link to the recording. So if this live session you want to learn more or repeat one chapter, you can see the recording afterwards and have a look at your own pace. Then I want to go to the go-to panel itself. It may look a bit different than yours, but we have two important sections here. This is the question section and the handout section. This is the important ones that you are all have on your desktop, should have. So the question section is for your questions. So please submit your questions here. And we have another premiere today. We will use the Vivado plugin. I will show you after this slide a QR code, and by scanning the code you have access to a question platform. And the difference between the question section on GoToWebinar is you can ask your questions, but you can also see another questions from all attendees, and you can vote for the separate questions, and we can highlight the most wanted at the end. So it's a little bit easier for us and for you. So I hope you can use both of them. So if you have also technical issues in the webinar, so please use the question section and we are help you out. So then the second important section, so it's the handout section. There you can see our training calendar PDF. Inside are all of our trainings, from seminar to power workshops to our long-term educations. There are several links to our website with more detailed infos about the agenda or the dates from the courses. Then one important fact by the questions is we are trying to answer all of them live, but if the time runs short or your questions needs a longer answer, we might get in contact with you afterwards via an email. So then I will show you the QR code. So you should see the QR code, so please scan it, and then you will go to the question platform. And there you are able to write your own answers and see all of the others. So I leave that slide a little bit for you. Also, I have the direct link in the chat section for you. You should see there the link to the Slido question platform also. So for that, I'm now over with the general part. I will happy it's now for you to present or to introduce you to the presenter today. It's my colleague Patrick Lehmann. He is a long-time trainer for PoC-2 and also head of system engineering. And despite his technical expertise, he also has a passion for open source. And with active roles in several projects like VHDL, or I hope I pronounce it right, it's IEEE 1076 working group. So he's a contributor for the future VHDL standards. And of course, this is why we have this topic today in our webinars, the PoC-Library. So I'm happy. Thank you for being here, and I hand over now to you.
Okay, thank you, Anna, for the short introduction. Is it correct? The Slido platform is without login, right? Just
yes.
Scanning, no login required, no credentials, just scanning and using the platform.
Yes, of course. Yeah.
Okay. Can we go to the next slide? So everyone should have the QR code now, right?
Yes.
Okay. Okay, so PLC2 as a company has a long tradition, mainly in training and coaching. In the past years, we developed like 3 big parts in the company that we are serving for. This part now is training and coaching and giving webinars or 3- and 5-day classes all around Germany and Switzerland. That's what we are mainly doing. In parallel, sometimes when the coaching is not enough and the needs from customers are bigger, then we also have development services. That's another foundation of the PLC2 company, what we are serving. And third foundation of the company is product development, sometimes also together with a customer. That customer is handing over complete product development to us, and we are working in close relation with them. I don't want to go into too much details, just to point out we are exclusive partnership or in an exclusive partnership with AMD for the German-speaking area as a training provider. So when you have questions for AMD technology, FPGA, and so on, NP-SOCs, SOCs, whatever it is, RF-SOCs, this is with us. We can offer all official trainings. We are also, it's a new brand with AMD, an official coaching service provider. And when it comes to the development services, we are a premier design partner with AMD, which also means we have matching access to internal data, documentations, and early access programs, and so on. Whenever you have questions around these technologies, just contact us, and we can help you out, I think. With this short introduction to PLC2 as a company, I want to go on with the training part, which is now a webinar. And as Anna said, it's one of my passions, working with open source. And I want to introduce to you the PoC-Library. This whole idea of the webinar here is to have a 3-parted series. This is now the first part, giving you an introduction in the library, what it is, and what we aim for. So I will talk about the history of the PoC-Library, the goals of the PoC-Library. Maybe you see the differences to other competing open source libraries, how it's structured and what we are aiming for. I will talk about version 2 that was released at FPGA Conference this year with lots of cleanups compared to the older version. I will give you an overview on some of the IP cores that you get a certain knowledge what is all existing, not diving too much into details. And with my main item, I want to dive further into the AXI infrastructure. That was the main contribution with version 2.0 that we released, as I said, a few months ago. And here I want to go into details on our AXI register, which is completely written in VHDL. And finally, I want to show up some next steps, how the PoC-Library and the contributions from PLC2 are going on in the next months and the next years, to give you an overview. Okay, so for the background information, let's talk a little bit about the history of the PoC-Library. So POC is not proof of concept. I know that lots of people think it's proof of concept. No, it's not. It's pile of cores. It's our collection of IP cores. And the idea is to have a generic and optimized IP core collection written in VHDL. It was initially created by Thomas V. Preußer and Martin Zabel at the Technische Universität Dresden, which was lately rebranded to Technical University Dresden. So here it was developed at the share of VLSI Design, Diagnostics and Architecture. I was also a part of the share, and we worked together closely in developing new IP cores, collecting IP cores we got from students, and we put it all together into one big library and started to open source it at a certain time. And now one of the maintainers of the PoC-Library, which is currently hosted on GitHub in the namespace VHDL. And for the creation history, actually it started already in 2007 as a collection of IP cores. And then in 2010, there was a certain transition from a collection of individual IP cores to a library. That means that IP cores are tightly coupled with each other, that interfaces are building up on each other. In 2015, we started open sourcing the whole library under Apache 2 license. And in 2017, I left the university and joined PLC2. And then we had internal further development. So my colleagues, of course, liked the library, maybe a little bit influenced by me, but they saw a certain potential in the library. So there was lots of internal development, using it also for own products, for own customer requests and consulting services. So we had lots of modules that are new. And in 2025, we started now publishing these internal enhancements and additions, and they are now going back into the public domain, of course, under the Apache 2 license, back to GitHub. And everyone can use them and profit from our contributions. The license of the PoC-Library is Apache 2 license. That's a so-called permissive license. To roughly summarize it, it means you can use it even for closed source. You need to specify that the PoC-Library is used in your project, that it's under Apache 2 license. You cannot modify the license itself and claim it's your copyright. And besides that, that's almost everything. So it's just about saying, hey, in my project, there is PoC-Library integrated. You don't need to name what modules you're using, to what extent you're using the PoC-Library. Just say PoC-Library is in your product. That's everything. No bigger requirements. The documentation is a Creative Commons license CC BY 4.0, which is an equivalent for documentations and for text, similar to the Apache 2 model, saying you're using it and you need to give attribution. That means who is the author of the documentation. That's it. The library itself is then mainly using VHDL 2008 because it's supported by almost all tools. We have internal knowledge which vendor tool is supporting how much of VHDL 2008 or even VHDL 2019 features. And depending on this, we have implemented certain algorithms or technologies based on VHDL 2008. So you need quite a modern tool to say it, but on the other hand, all major brands are now supporting this language revision. It's similar for synthesis and simulation. There's no big difference. We aim to be efficient and resource friendly with our implementations. In many cases, we can figure out what FPGA device is used underneath, and then algorithms are fine-tuning based on the selected platform. And we might change the internal algorithms and implementations. Let's say if this is a 4 lookup table FPGA or 6 input lookup table FPGA. The IP cores itself use standard and generic IP core interfaces like AXI. I will come later to this point. And in other cases, we might have enhanced interfaces that are optimal for synthesis to be, as I said, resource friendly in the overall implementation. Our IP cores have lots of configuration options. That means you can enable and disable features. You can select certain algorithms. You can select how many resources are consumed. You can set up pipelining and timing parameters, whatever you like. So there are lots of options if you compare this to integrated IP cores with certain IDEs, where the number of configurations options are quite limited. We have lots of options that you can fine-tune the IP core to your design needs. And as I said before, it's all automatic and transparent inside. So when you select your target, it's then changing internal implementations depending to the needs. And the last goal of the PoC-Library is to be independent, to show you what I mean with independent. We are independent of the implementation for certain device vendors. So it's independent of Altera, Lattice, AMD, whatever you have. We are independent in the technology. If it's an FPGA or ASIC technology, we try to be independent of tool chains. So simulation, synthesis, and so on, everything is supported. And we also want to be independent for the host system when it comes to your operating system. Independent if this is Darwin or macOS, Linux or Windows, the scripting is made in a way that it works on all platforms equally. Of course, you need to have the matching tool chain running on such a platform. Okay, then let's go to PoC version 2, which is somehow a restart of the PoC library. There have been certain years where there was almost no activity with the PoC library. As I said, it was just internally at PLC2. Of course, it was not visible to the outside world, and this is what we want to change and give you now more insights, what's going on, what we modified, and what we will do next with the library and how PLC2 is contributing to this library. So the first step in the transition from the old version 1.2 to version 2.0 was forking the PoC library under a new namespace, which is now at github.com/vhdl/PoC. We uploaded here certain enhancements and cleanups, version 1.3, 1.4, and as I said now, version 2.0. Currently, version 2.1 is in review. We waited for NBC for an update in the simulator that the pipeline is now finishing, and there's another documentation page we want to add. Otherwise, everything is ready that we can have a version 2.1. The CI on GitHub Action is running with VHDL and NBC in parallel, and we are using OSVVM for our verification environment together with the OSVVM scripting. The documentation of the PoC library is also published on GitHub, vhdl.github.io/PoC. And this is one of the big points we want to improve in the future, writing more documentation and more details to it. When it comes to a maybe question, what is about the existing code that the old PoC library had and with our new contributions? Our goal was, and as far as our tests show in our regression testing, that the existing code was never degraded. We just added features, we added bug fixes. And of course, the test benches are not fully working yet. We are in the transition from an old system that we had manually written now to using a verification framework, and we will have tests based on OSVVM. And when it comes to other modifications and additions, we use still the same abstraction techniques that are existing in the PoC library to be vendor independent. So all new IP cores are based on the foundation of the older PoC library. So previously, as I said, we had support for different tools, different synthesis tools and simulation tools were supported. And with the current enhancements, we have tested with AMD Vivado, Aldec Vivera Pro, Siemens QuestaSim, VHDL, and as I said now also with NBC. And we aim to expand this support. It was already supported in the past, but there's a certain environment we need to set up and run all the regression to prove what has been changed in the last 7 years. So we might need some time here, but it's still on the agenda to test everything again. And the old internal scripting from PoC library called IPCMI will be removed and phased out step by step. And we are using right now OSVVM, and later it will be combined with EDA Square scripting. Other changes from the old library is dropping some support. So we dropped Xilinx ISA support. Last release of Xilinx ISA was 2013. So 12 years later, we are now dropping support for ISE, Plan Ahead, and some devices from the series before 7 series. So Spartan 7, Vertex 7, Kintex 7 is still supported, but everything older is for now kicked out. If you need this, you can still download version 1.2 and you get it as it was before. The old library integrated lots of different verification frameworks because there was a time when verification frameworks were growing. So we had their UVVM, VUnit, and CocoaDB inside. Every framework itself is now quite big. There are standalone big frameworks. I think there's no fostering needed. So we kicked out UVVM and VUnit, and CocoaDB we need to review. There's one test case inside that was written with CocoaDB. If we keep it or not, that's still under investigation. This removal is not due to technology. It's about keeping PoC small and streamlined and not being a collection of all VHDL code out there. As I said before, we have lots of bug fixes. It would be a presentation in itself to talk about bug fixes. So you can read our changelog if you are interested in this. And another big change was moving the synchronizer components from the MISC namespace into a main namespace directly underneath PoC, which is now PoC.sync as a namespace. This is due to the importance of synchronizers that was maybe not seen in the past when we worked at the university, but nowadays designs have different clock domains, so it's very needed to have synchronizers. Okay, so let's talk about IP cores. What do we have inside? What is the content of the PoC-Library? So first, a library always needs packages with different data types and helper functions. So just to name a few of them, to give you a rough overview, we have a utilities package, which gives you an is simulation constant. So PoC-Library can figure out if your code is running in synthesis or simulation. And with this knowledge, we can fine-tune the internal algorithms, or we can reduce runtime in simulation. Let's say you have a stopwatch and you want to run it with seconds resolution. No one needs nanoseconds. So counters, instead of counting to 100 million, can just count to 100. And this is done as code with an implementation using the function ITE. That's the function I have here at the end, which is a ifs and else construct combined with is simulation, and then you can switch constants in your code depending if it's synthesis or simulation code. Then I think every library somehow has a helper functions to get the number of bits you need for a certain number of states you want to encode. In our case, it's called log2seal. So it's logarithm2 with sealing function combined. We also have conversion functions like binary to one hot, binary to gray, and in reverse. Just to give you a rough overview, I think it's multiple hundred helper functions in there. If you're interested in this, just contact me, read the documentation, or have a look into the packages to see it. There's also a discussion channel on GitHub. If you're familiar with this service online to have discussions for Git repositories, OSVVM, VUnit, and other frameworks are available there. There's also a discussion space for VHDL questions in general, or the PoC-Library. Then we have another helper package, which is called vectors. So we have a certain implementation of standard logic vector and standard logic vector data types. There's also standard logic matrix data type and hundreds of conversion functions forward and backward to convert from linear to two-dimensional to one-dimensional arrays. So whenever you need to handle vectors and matrix implementations for bits, we have a matching data type and lots of, as I said, conversion functions for it. And finally, for the discussion of packages, we have a physical package. Maybe you're familiar with VHDL, that there's only one predefined physical data type called time. We made further implementations, so there's a memory data type and a frequency data type. And with the frequency data type, we have conversion functions between time and frequency. And you can have all these calculations based in either frequency domain or time domain. And finally, the most important function there is timing to cycle. You specify your baseboard frequency, let's say 100 megahertz, timing, let's say a debounce time of 3 milliseconds, and then it's calculating for you how many clock cycles you need for your counter. And this is quite handy function when it comes to physical interfaces and implementing a certain timing behavior based on counters or state machines. And for basic components, we have synchronizers for everything that's related to crossing clock domains. There under the hood, we have vendor-independent synchronizers at first that you can instantiate in your design. And as I said before, there's a certain configuration with your FPGA part name in the library itself. It figures out if you're using a Lattice device, Altera device, or AMD device. And based on this, we might have specialized implementations that improve on a certain platform, the MTBF, have special timing constraints, placement constraints, whatever it is, depending on the documentation from the vendor and our own knowledge and experience, what is best to implement synchronizers. The synchronizers itself are categorized into either 1-bit or n-bit operations, and as a signal you are transmitting a flag signal, which means it's long time stable, or if it's a strobe signal, which is active for 1 clock cycle and then it's inactive again. There's a documentation page in the PoC-Library with a table giving you then a 2-dimensional matrix, and you can decide on your use case what synchronizer to use best. We have an abstraction layer of on-chip memory, so-called OC-RAM and OC-ROM. Again, this is vendor independent of the memory description. It can be synthesized to distributed RAM, block RAM, ultra RAM, or M20K, or whatever other modules you have. The RAM or ROM can be initialized with memory files like MEM files or MEF files, and we are supporting single port, simple dual port, true dual port, and some other variants of it. It would be too much to explain all details here, but again, based on the FPGA part string, we are then selecting the matching implementation. All modules have the same timing behavior. That means when you're writing in 1 clock cycle and you're reading in 1 clock cycle, whatever implementation you have, the timing behavior when it comes to full clock cycles is the same on all platforms. And this would enable you to go with a generic VHDL design from vendor to vendor and have the same timing behavior. And finally, for some basic parts in here, we have FIFOs. There's a generic FIFO, there's a CDC FIFO, as I think every library should have. We have a special one that's called FIFO Glue. In case you need to have a pipelining stage, that's the shortest FIFO you can implement, only with 2 stages to break the timing critical paths in your design. That's our FIFO Glue, to glue components together. We also offer temp put and temp got FIFOs. That's with transactional behavior. This is useful for packet processing in case you need a FIFO that is supporting retransmission, so you can reread from a FIFO, or you have a receive FIFO where you have CRC computations. Then it's a temp put FIFO. You temporarily write into the FIFO, and when the CRC is correct, then you acknowledge the data in the FIFO for further processing by later components. We also support so-called gearboxes. This is mainly used in bus infrastructures when it goes from 1 bit width or bus width to another. Let's say you're converting from 32-bit to 64 bits. We are offering this either with a fixed clock relation or with independent clocks to each other. We also have low-level communication components like CRC computation for whatever polynomial you want to specify. We have scrambler implementations. Further data structures are like stacks and double-ended queues if this is needed for your algorithms. And we have a generic implementation for a cache, a tagging unit, and the replacement algorithm inside of the cache. Currently, we have an LRU, so the least recently used algorithm implemented. So these are the basic IP cores we have on there, and from there we can go on and build higher level other IP cores. Maybe also arithmetic IP cores can be considered as a foundation. So here we have converters between binary and BCD. We have a wide adder, so in case you need an adder with more than 256 bits, which is performing better than a ripple carry adder, pseudo-random number generators, so a PRNG, dividers, scalars, square root, barrel shifter, to name just a few of them. In arithmetic, we also can put in sorting networks and sorting algorithms. So we have an LRU cache implementation, an LRU list implementation, Bitonic sort, odd even, merge sort, and some others. And in the category of arithmetics, I also have for you statistic modules when it comes to average computation, histograms, minimum and maximum computations. We also have algorithms for this one. When it comes to I/O, we have an abstraction layer for DDR I/O cells of FPGAs. So again, here that's a low-level component. If you have an IP core that needs to transition between different platforms within one vendor or even from vendor to vendor, we have implementations here. Of course, I think every component library somehow has a UART implementation. We have an I2C and SPI implementation that's on our release list to improve the code here and to release it. Similar with MDIO for talking to Ethernet PHYs. There are certain modules available for PMODs. These are extension modules from Digiland, a frequency counter, debouncer, glitch filters, PWM generators, and timing counters. Timing counter is some kind of optimized implementation when it comes to, let's say, waveforms you need to generate. So we have an optimized implementation. For networking, we have an Ethernet stack with NIC layer up protocol IP version 4 and version 6, ITMP, UDP version 4 and UDP version 6. Currently implemented for up to 1G, and maybe let's see what the future is bringing for further speeds. This was so far the summary of IP cores we have inside of the PoC-Library. Now I would like to come to the contributions that PLC2 did in the past. And one of the big topics is the AXI4 Lite and AXI4 Stream infrastructure that PLC2 developed internally and which was now open source. So with AXI4, we get, of course, packages and new data types for the AXI4 infrastructure. We have a FIFO that's implementing directly the AXI4 memory mapped interface, including a staging option. So in case you need a stage just to decouple the critical path on AXI4, this is available. The stage parameter can be 0 to deactivate it, can be 1 to activate it, but you also can set up higher numbers. So in case you need to go from one end of your FPGA to another end of your FPGA, for pipelining, you can set up any arbitrary number. Let's say you need 4 stages to cross your FPGA, it's possible. It doesn't need to have any copy-paste code on your side. It's just a parameter you can fine-tune. Of course, we also have a CDC implementation, which is based on the FIFO from PoC that is for CDC, and this again is based on the OCRAM. So we are now in a third layer of abstraction. Hardware-specific implementation OCRAM, CDC, FIFO, and PoC, and now we have the AXI4 CDC FIFO implementing a certain protocol. We have an adapter from AXI4 to AXI4 Lite if you want to go to a configuration bus architecture. And for team working purposes, we also have so-called terminations. The idea here is if a certain IP core is not yet implemented or your colleague is working on it, you can have a termination module that you don't have any open ends in your AXI infrastructure, and later you replace the termination module with the real implementation of your subsystem. Similar, we have these components for the AXI4 Lite protocol, which is a strip down of AXI4 itself. So again, FIFOs, CDC, FIFOs, we have an adapter to OSVVM when it comes to simulation. So we can directly interface with OSVVM test benches and the verification components. And we have a generic register implementation, which I want to show on the next slides with some more details. The idea here is that the register is not generated by some external scripting. Everything is written in VHDL. Maybe it's also my own passion to try to solve complex problems in VHDL and test the language to the boundaries. and we want to show that this is possible and what features we can implement here. Finally, for the Axi4 infrastructure, there's Axi4 Stream, again with FIFOs and different FIFO variants, like with temp put and temp got feature set, so this temporary writing and temporary reading feature, CDC FIFO, of course, stages, and for the Axi4 Stream infrastructure, we also have multiplexers and demultiplexers when it comes to directing data streams in your design. Another upcoming part that we are currently discussing internally to release it is multiplexers and demultiplexers for the Axi4 Lite and Axi4 infrastructure. So to get these two protocols in parity with Axi4 Stream for address multiplexing. Okay, then let's talk with some more details about our register, which will be also part then of the second webinar next week, same time, same place. There you get an introduction into how to use the PoC-Library and how the register can be used in different use cases. So my part now is a little bit more theory, show you what we have as features. Of course, we also repeat this next week, just to give you an idea what we can do. And next week you see then how it's used in real life. So our Axi4 Lite register, as the name says, an Axi4 Lite interface, it's supporting 32-bit and 64 bits operation in parallel, depending on what data type you connect or what bus you connect to the register. It's automatically figuring it out. In case you have the 64-bit bus connected, then you can have single access 64-bit register reads, which means you're always reading a double 32-bit register. It's quite easy and flexible with the interfacing also when it comes to the software access. And we are working on exporting the configuration from VHDL. Currently, this format is writing out a CSV file from synthesis to your disk, and then it can be post-processed. As CSV was the original idea to get out some data, we found a better way, which is based on YAML writing. So there will be an update with one of the next upcoming versions where we are writing the full register configuration, so register names, modes, bit sizes, and so on into YAML code. And we will have a conversion script from YAML to C and C++ structs via a Python script. And this will allow you to integrate the register description directly in your compile flows, let's say into a GCC compile flow, or G++ if it's C++ structs. The description of registers is completely done in VHDL. So we are using VHDL code constructs like ifs and else statements, loops, functions, and generics. So you can add registers or configure registers based on generics, even from outside, like top-level generics to your synthesis. You can connect it to your generate statements. This is all possible. So we are quite flexible. And another feature is we have built-in interrupt support, so you can specify certain registers to capture events. And if this is the case, we are setting an interrupt mask, and you can read out what happened in the register. So for the feature list, we have, of course, read-only registers, read-write registers. These are the common ones. And now we have some optimized further modes. One is a constant value. So it's taking a value from the init field of our register description. And this is like connecting a constant or generic to register. This is quite useful when it comes to, let's say, a Git version you want to encode in your registers. At FPGA Conference, we also had a presentation about this feature. It will be also part of next week, where we show how to read out Git information, branch names, hashes, and so on, compile time, puts us into code and into generics, and then we can connect it to the register with almost no overhead. We also have a mode called read-only or read-write not registered. So usually, as the register says, every data is registered and then it's fed into the Axi4 Lite bus infrastructure. With these modes, you can have like a false rule. This is quite interesting. Let's say you have a UART implementation with a read FIFO and write FIFO, or transmit FIFO and receive FIFO, and you want to have no further delays in your operation. So you can specify one address, or actually multiple addresses in your register space, and connect them to FIFOs, and there's no additional clock cycle in the delays. And it's again saving resources. The latch value on high bits and low bits mode, this is for interrupt capabilities. So this is quite nice when it comes to error flags and states. You can latch them in the register, and then you can specify how to clear the latched bits in such a status or error register, if this is based on a read operation, on a write operation. So you can define with the configuration and with your software how you want to clear the latched bits. So for our ports, what do we have? It's quite simple. We have clock and reset, the obvious signals you always need. We have 3 ports for our AXI connection for the AXI Lite protocol. We have manager to subordinate. That's one record for all forward signals. Then we have subordinate to manager S2M as a port for all the reverse signals. And then we have an IRQ signal for the interrupt request. On the fabric side, we have a write port with a write port hit, and then there's a read port and a read port hit. Write port is a 2-dimensional vector providing data from PL to the internal registers. When it comes to naming convention, there's a certain time where you need to decide, do you look from software side or CPU side, or do you have a look from the fabric VHDL code side? We decided to look from our VHDL code into the register. That's why the write port is from fabric to the register, and the read port is in reverse. The dedicated signals called underscore hit are giving you a one-time or one-cycle active bit whenever there's a read or write operation on a register. So your user code doesn't need to figure out a register has changed. You get notified in the fabric if there was a write operation or read operation on a certain register, and then there's one active bit in this mask. And the write port strobe, that's a one hot encoded vector where you can give updates to the register itself from fabric side. When it comes to the generics, there's one big configuration, which is our register configuration itself. That's a vector of register descriptions. I will show this on the next slide with some more details. We can activate interrupts. You can specify where the interrupt registers are located. Defaults are the first 2 registers. You can specify if you want to init the registers on reset or not. In case you don't need the reset feature, you can save lots of resources in the register. You can ignore certain high addresses in the register itself, and you can specify the error response code depending on your environment. Okay, so internally the configuration, as I said, has different modes. I want to skip a few of these. These are lots of implementation details. You have the recording and you have the documentation to read more about it. Just want to point out we have lots of different register modes in here, which are then summarized into a record with the name, the address, the mode, the init value, and how to clear mask, and if it's a interrupt register. And these records are then summarized into a vector, which is our TAXI4 register vector describing the whole register. When it comes to using it, instead of assembling the record yourself, we have a helper function called TOAXI4 register, where you hand over the parameters, and internally it's then filling out the record data structure for you. Also takes care of some default values if you're not using a certain feature. So the easiest way to use it is TOAXI4 register with a name, an address, and the mode, and that's it. That's all you need so far for configuring individual registers in there. Let's use the last few minutes for some simple examples. And as I said, next week we will dive further into more details. So the first implementation here is a single 32-bit write register. We have some helper signals we need here. We have the instantiation of our register, as I showed you, with the common signals, the AXI port, and then our read and write ports here. We are configuring our register, and in case it's just a single register, you can write an array directly into the generic map, like this one here, specifying the read-write register with a name, the base address, that's it. And now you have already a single 32-bit read-write register. For accessing it, let's say you have some data you want to read from the register and use it in your software, then you can extract it with a read port bit 0, or you can write from an FSM with a write stroke into the register and update the register. For a little bit more complex configuration, let's take the same register, but this time I'm using a constant to help me here with a more complex configuration pattern. So let's set up our register configuration, which is this register description vector. And this is now an array computing with multiple calls to 2 AXI4 register description, our configuration. So we can set up a control register, some length registers, we can even reorder them here. You see here the addresses are not ordered. Of course, we all try to write nice code, so you would do it better than me here. I just want to express what's possible with setting up registers. We have here our modes, and the first one is even set up with the auto clear mask now, so the lowest bit can be cleared. We need some helper signals in here, and as I said before, the output ports are vectors of vectors, so we are using from PoC-Library the TSLVB array of 32-bit arrays. We are constraining them here, and now we can connect it. When it comes to using registers, instead of remembering that your control register was the first register to index 0 in your design, we have a getIndex helper function where you hand over the name of the register, the data structure for the configuration, and now you can access individual bits or data words from your register based on names. So in the background, we have a lookup in our data structures, and we can figure out the index for you, and we have more abstract and readable code in the overall design. My last example wants to stress again on AXI for UART. For UART Lite implementation, we are taking the same interface as the AXI Lite UART shipped with Vivado. So we have 4 registers. We have an RX and the TX registers for the receive FIFO and transmit FIFO, and then there's a status and control register. We are setting them up here with the addresses incremented always by 4. That's the count we need for 32 bits. And we are setting up the modes. The first 2 ones are in this fall-through mode, and the last 2 ones are set up, one in read-only mode and the other one in read-write mode. So we are using here now 4 different features of our register. We have some indices, so if you want to reuse them, instead of calling the function multiple times, you can also save them in constants to enhance your code quality. And then we are accessing the individual words of our register, and then even here individual bits, and we are then implementing the UART Lite register and bitmap as it's done by Vivado in their IP core. And now we have a compatible implementation, and I think next week we can show you more details on this one. So far for my introduction into the PoC-Library, we talked about IP cores that are in there, we talked about packages and helper functions, and now I even showed you what has been contributed by PLC2 with the AXI4 infrastructure, and with one detail here on the AXI4 Lite register itself with certain configurations and features we have, and we will deepen this knowledge and what we can present here in the next weeks. My last slide is about what we are going on with the PoC-Library, what will be new contributions. As I said before, we are adding more and more tests. We have them already in Germany. There's some fine-tuning on the test. We will work definitely on the documentation because documentation is very important. But you all know writing documentation is time consuming, so that's an ongoing process to enhance it. We will also integrate our test reports as an appendix into the documentation, even with code coverage if possible. We are enhancing the tool chains we are supporting, so we want to roll out the tests that we had in the past, also running with Quartus and Diamond, and we want to upload more IP cores, as I mentioned before, the Axi4 Lite UART, I2C, SPI, MDIO. This list here is still showing the Git version register. This is already done. It's part of the new version 2.1 that's currently in review and finalization. So this slide was originally from FPGA Conference. So we have checked off one item already, and you see there's progress in the PoC-Library. And we are aiming for somewhere in future to have a version 3.0 with more refactoring and simplification of interfaces. So we will have more cleanup in here to get better streamlined and focus more on common interfaces like the Axi infrastructure. So far from my side, and now we have still 8 minutes left for some questions, and I will hand over again to our host Anna. Thank you very much.
Yeah, thank you too for the insight and overview of the PoC-Library. And before we start with the Q&A, I want to show you the few important links here. Maybe you already know the FPGA conference. So here's save the date for next year. And in short words, this is a 3-day conference. It's filled with training sessions, keynotes, important speeches, and an exhibition hall also, and a really cool evening event. So please go to the link and save the date or read more about that. Then our LinkedIn account, also stay up to date with PLC2 and all other stuff like the development service or our product and our trainings, of course, and the webinars they are upcoming. And then we have the development service QR code, as Patrick already mentioned in the introduction. We are also support you in your projects. And if you need help there, then please use this code. And then the fourth code, the black one on the right side, is about the second part for next week. So don't forget to register for that. And we are happy to have you next week here also. And then I think we have that, and we have a look on the questions.
Yes, so for FPGA Conference, since 8 or 9 years, I had lots of PoC presentations already in the past, and it's planned also for next year to have, I think, at least 2 or 3 presentations on PoC-Library and related technology. Yeah.
Did you already see some?
I have here one question asking for different clocks, but I'm not sure what the context is of this question. For different clocks. So the FIFOs itself, we have single clock FIFOs, or so-called common clock, and then the CDC FIFO, that's with 2 clocks. Can be related, can be unrelated clocks with each other. Similar with our synchronizers, they're usually for unrelated clocks with each other.
Okay, then other questions are, let me show you.
The TDB RAM. So that's, as I mentioned, it's an abstraction layer, the true dual port RAM. We are supporting any data widths. It's depending on the vendor, we are using synthesis inference. So you can have any bit size, if this is 9-bit, if this is 17-bit, or even 259 bits, whatever is working, and supported by synthesis. With some tools, we figured out they have sometimes problems figuring out a good combination of block RAMs to align them side by side and in length to get to the matching area. So when you have memory or the size of a FIFO, you're always RAM, you're always describing an area. So we have certain optimizations inside. You can also enforce the type of the OC RAM and what is the FIFO relaying on. let's say you have an ultra scale device and they are ultra RAMs free, and synthesis is always deciding to use your valuable block RAMs. You can enforce and say there's, let's say, a video image pipeline line buffer or so. You can enforce it to use ultra RAM, to use these resources and not block RAMs. That's possible. And when it comes to clock speeds, that's purely related to the speed what your FPGA is supporting. So usually it's multiple 100 megahertz. That's common. Okay, how is the index function implemented in RTL? So the implementation of the get index function is, so the configuration was an array. We are looping with a simple loop over our array, and we are comparing the register name. Depending on the tool, it can be fast, it can be slow. We are also in discussion with certain vendors to use the register implementation and the lookup functions for profiling the synthesis code, because we figured out that certain tools had problems in string handling. Keep in mind, everything you do with constants, computing generics, and so on is done at elaboration time. It's not at runtime, or it's not in your chip runtime. So actually, you can do anything in elaboration time as long as you figure out certain constants that are used to describe your netlist of the design. So yeah, that's why we have the lookup function. The carrier string is left. I think then this question is answered. Open logic differences at the end of the present. Okay, so open logic is quite a new library. I also met with him at the FPGA conference, and we talked about certain strategies and how both libraries can align or how they are overlapping. So we are not like split apart like OSVVM and UVVM. We try to cooperate and find a common ground. So that's one thing. Another one is when it comes to the license, I think our license might be more suitable for certain projects, because we're using Apache 2 license with a permissive license model, while OpenLogic is using a GPL license with a linking exception. But this means you need to read the linking exception, understand it, and have it cleared by your company or by your legal department. It's a bit different on the Apache 2 license because it's a non-modified license. There's no additions to it. So whatever Apache 2 is saying and what your legal department already knows about the license is what we use. No extra legal code to it. It would be nice maybe in future that certain libraries that are existing can work closer together and we find a more common ground. We also had a quick talk about these helper packages and data types if we move them together. So PoC-Library and OpenLogic would be based on IP cores, where they have certain strengths in their own. But when it comes to shared data types like vectors of vectors, matrix data types, binary to one hot conversion, whatever, if we can share this in one library and both frameworks can benefit from it. I don't know, is there constraint support? So the CDC modules always come with XCC files, or depending on what vendor you have, also SDC files with timing constraints. It's all part of the library, so you don't need to write the timing constraints yourself. We are using relative timing constraints, so it means you specify the timing constraints once per entity in VHDL, and then the tool, let's say Vivado, detects that the FIFO is implemented or instantiated multiple times in your design. It's replicating for you the CDC settings. Everything is done automatically, and we are investigating the idea of changing from XCC to Tickle itself because it has certain advantages. Yeah, that's in discussion. Then is there another question that popped up?
No, this is the last one. Oh, no.
The documentation that it shows version 1.x instead of version 2.x. That's a nice feature from GitHub. So there's also a timed pipeline. and this is currently overwriting from time to time the documentation. That's something I need to fix. So there was already the version 2 documentation online, but sometimes an older CI run is kicking in and overwriting this older documentation. I need to figure it out and get it fixed. How do synchronizers differ from XPN macros? I would say, how do XPN macros differ from PoC synchronizers? Because we have been first, and then Xilinx came up with XPNs. Maybe they didn't know about us and that it existed, but the PoC synchronizers should be older. And another one is XPM is only working for Vivado. Our synchronizers are working the same way on Lattice and on Altera. And also we want to check it with Cologne FPGA if it's working on their devices. So you can switch the design from vendor to vendor, and XPM would be a login again just to Xilinx and Vivado, or AMD and Vivado. If we have an import function for YAML, that might be complicated. So right now we know that certain tools are not supporting reading external files. So Quartus is rejecting any support for string operation and text operation in files, despite having support in Verilog and in VHDL, so the Altera HDL, but they are claiming that it's impossible to implement this for VHDL. And as I said, they have already 2 implementations. So that's a problem here. And another one is the heavy string processing. Because it's running at elaboration time, we are bound to static memory allocation and array allocations. What I figured out so far, at least when it comes to Vivado, there's a new insight since 1 month that they are supporting protected types in synthesis at elaboration time. And I want to experiment with this feature. If this really works out and we can have even maybe dynamic memory allocation with a new operator in VHDL, then I see a very high potential for also reading YAML or whatever other data type as an input. That would be nice. So this is up for experiments to work on it. I'm also now in closer contact with someone in the development team for Vivado itself and synthesis. We are talking about certain features that are existing, and he gave me the hint that the protected type is now available in synthesis, and I will check how far it's working and what benefits we get. I think this is the first vendor that has managed to implement it, and if it's really working, then they have invented the holy grail of VHDL programming. An external tool, Python for content. YAML to VHDL. Our idea is, and there are again different philosophies that exist. Either you have a configuration file and you have a code generator generating VHDL code, and then your single source of truth is outside of VHDL. Our idea is to have the single source of truth inside of the synthesizable code, which means inside of VHDL. That's why we have the description inside. One of the advantages is that your source code is not modified. Otherwise, you have generated code, and when it comes to Vivado, for example, and a few other tools, they are upset if the timestamp has changed of a file, and then it's invalidating your synthesis results. So whenever you're running and generating it again, you need to re-synthesize everything. It's a bit unfortunate when it comes to it. Even if there's no type or data change inside, or no configuration change, just by the timestamp, because it was updated, certain tools want to rerun synthesis, and we are avoiding this by having the single source of truth inside of VHDL. And yeah, that's just a philosophy, and we try to use this approach. And we also showcase what you can do with VHDL.
Okay,
I think
one last question. I think this was in the latest.
Older versions and With Quartus, we don't need relative timing constraints, because as far as I know, they are not supporting relative timing constraints, but they have a better feature. You can have a VHDL attribute inside of your CDC component with embedded SDC code inside of a VHDL attribute, and this is then relative to the entity. Have a look inside of the PoC-Library, go into the synchronization directory, so PoC-Sync directory, and there you find sync_bits_altera implementation, and there you find an embedded STC command inside of a VHDL attribute. And this was working like 10 years ago already, so that's very old stuff. Okay.
Here's some question about AMD Vivado support.
So the Vivado support, I would say, is one of the strongest, because PLC2 is, let's say, 99% working with AMD Vivado. So everything we do here is tested with Vivado, also certain versions backward. So whatever we have as features is supported at least from 2018.3 onward.
Okay. Yeah. I think we are close now.
The last one is it recorded?
Yes, I want to say that. Okay, for someone who missed the beginning, this session will be recorded, so you will get a follow-up email with the direct link to the webinar. And thank you all for joining. And if you have any questions last minute, the room will remain open for the next 5 minutes. So we can answer your questions afterwards via mail if you want. And one important thing is let us know what you think. So when the webinar ends, there will be a survey pop up. So please let us know and give your feedback. This is very important to us, so we can improve and make the webinar better, especially today with the Slido plugin. Tell us what you think. So from my side, that's all. Thank you all for your time, and have a good day, and see you hopefully next Tuesday.
Yes. See you next Tuesday, same time, same place.
Yeah.
Bye.
Bye.